All right, recording is rolling. It is Thursday, April 11. Gonna get into capacitors, inductors, and electromagnetic induction today. It's gonna involve generators, motors. Tomorrow, I'm gonna have you guys do 3 mini labs. I'm gonna have you guys build a compass, build an electromagnet, and build a motor. And actually, I'm gonna demo those for you guys right here. So today I have some demos, I have some new posters, I have some videos, and just to avoid switching back and forth, I'm gonna kind of do it that way. So I'm going to do all the demos first, and then all the posters, and then we'll switch over and do all the videos. Okay. So let's start with how about a compass? So if I have what this? I got some bar magnets. Right? I'm gonna have you guys build this tomorrow. So pay close attention here, so you guys know what's going on by tomorrow. Okay. And I know where the poles are on these magnets. Maybe we can kind of figure it out with the help of this, right? Say like, what does this look like? Right? This magnetic field. Right? Now this would be like a 2D cross section of a magnetic field, right? The poles are on these faces. So there's like either a north or a south here, and the opposite, either south or north right here. If I break this apart, it's just a smaller version of that. Here's either north or south, here's either south or north, right? Depending which way, right? If I put this together, it's effectively one giant magnet now, right? The magnets will always have these two poles. I can show you guys the 3D version of this. Right? There's a magnetic base right here. So that's a magnet. I got these iron filings, right? So, right? But ended up it's like a sand timer. Now this works, I think, better in person than on video or through a screen. But if you see this up close, you can see like a 3D magnetic field. Ooh, okay, so great. So we've got a magnetic field. And we're all sitting in a really weak magnetic field right now, which is Earth's magnetic field. Right? More on that later when I show you guys the. It's like, why does Earth have a magnetic field? Probably something to do with Earth's molten um, mantle and convection currents. Right? But more on that later. Right? So we've got a magnetic field, and I might wonder, like, hey, which sides are north or south in this magnet, and for that matter, like in this room, like which way is north? Ooh, how about that? That's a good trivia question, right? Uh, Here, everybody point north. Which way's north? Which way's north? Oh, yeah, you guys know. Yeah, there you go. And so north is kind of like that way, you guys are saying, right? True, true. Right. Oh, and how can I show that? Well, tomorrow I'll give you guys a couple of cups, put some water in one cup, right? And then in the dry cup, notice in the dry cup I'm putting magnets. And I have them so that the poles are oriented horizontally. You guys see that? Horizontally oriented poles? Now if I put this in this water, right, let it go, it will naturally align north, south, right? Right, so there you go. So there's north, there's south, right? Now, even if I rotate this to a different orientation, right? It's a shade. I might need a little more water in this, right? I think a little more water would be helpful. I'm gonna put a little more water in here. Time out right here. Too much you don't want to spill, but let's try this again. Ah, yeah, there's a better compass right there. See, it always orients the same way, right? And do you guys know north and south attract and south and north attract? Right? North and north repel, south and south repel. Right? You guys know it too, right? Now, hundreds of years ago, people did not know that. So they said, well, the side of the magnet that's always pointing north, right? This could be a compass. Right? You could also do this with a string, by the way. So, right? But it's basically a compass. Right? Let's call the side that points north the north side of the magnet. Right? Now, again, they got that convention exactly backwards. Oops. Right? So what that effectively means is that Earth's magnetic north pole is, guess where? Canada or Antarctica. Magnetic north is actually in Antarctica, and magnetic south is actually up in Canada. Right? So it's kind of backwards. Right? So that's what's magnetic north is opposite of what's geographic. Right? Okay, so there's a compass. I need to show you guys what's next. Electromagnetic. I mean, and have you guys tomorrow. Right, so over the class today, you guys will see like more like why this works, but just to show you guys put this together. Okay. Say I'm going to have this bolt with a wire wrapped around it. This might be called an inductor, right? All that wire wrapped around. Notice it's insulated, so it can't like short out. So right. Whatever current I get flowing through this wire is going to be forced around that loop. So let's get, okay, so I got a battery here. I got some paper clips. Right? Now, right now, this is not a magnet, right? Not any kind of magnet, not a permanent magnet, not an electromagnet. I can try to pick up these paper clips, nothing, right? Nothing, right? Right. But watch what happens when I attach these leads. Notice I got stripped leads, right? Okay. And tomorrow, if you want to strip some leads, a good way to do that is to take some scissors and so very carefully make an incision all the way around this plastic insulation, and then very carefully pull off that plastic insulation, right? So that I can make contact with leads of a battery. They might say, does this short circuit? Technically, maybe. So I won't do this very long, right? But otherwise, it'll get hot kind of fast. But I've got hooked up to this inductor. Right? This should create a magnetic field, right? And I should be able to pick up this paper clip. See if it can. There you go. Right now, that's an electromagnet. So it's only a temporary magnet. As soon as I disconnect the battery, it's going to lose its magnetic power. Right. So like that. Right. And then disconnect the battery. Bam. Right. And then the paper clip drops, and I can't pick it up anymore because I disconnected the battery. Right. I see it. Right. So there you go. So that's an electromagnet. And what was the third? Oh, motor. Right. So a motor is, see, if you can get a current flowing past a magnetic field, that will actually create a physical force. Later on today, I'll pull up a poster that says right-hand rule on it, which tells you the directions that are involved with this. What I need for motor. I need these items right here is what I need to make a motor. Okay. So I've got a battery with no leads extended. Okay. I've got, what's this? I got a coil of wire with, again, the ends are stripped. And just for, here, I'm gonna say this again, right? Like, what's a good way to strip this? Because like over so many years, I've seen students like try to strip wires. A really bad way to do is to take the scissors and just go like, That's really dangerous because now you got these sharp blades and you got like no control and there's like eyeballs nearby. Right. So that's not good. Right. But if you just very carefully make an incision, just go around and then very carefully pull off the insulation. Right. Great. Now you got both sides. You got a couple of leads. Right. And then all around the inside, it's insulated. Right. I got the extended leads with these paper clips right here with this battery. Right. So I got 1.5 volts right here. I'm just going to connect this right here. Again, I don't want to leave this like this because it'll short out the battery for too long, but for a little bit, I can take this, right? So now I got a current flowing around. If I put this next to this magnetic field, see if I can get this to rotate. There you go. You guys see it rotating? So there's a force. In fact, it's rotating a specific direction, right? Oh, guys, how long could that rotate for? Until the battery runs out, until the battery drains, right? There's a finite amount of chemical energy in this battery that's being converted to, well, electrical energy and then back to mechanical energy, right? But yeah, there's only a finite amount, so that won't last forever, right? Now, when you guys are doing this tomorrow, a really good tip. Again, I've seen students do this so many times over the years. So you guys see how the two leads of this motor, I could draw a line between them, go right through the geometric center of this loop. You see that? Okay. So that when it's resting on those paperclip leads, it doesn't really have a preference, at least not a strong preference, which way it hangs, right? Versus a really common mistake I'll see students is if they have the leads like this, right? And then if they have them like that, where it doesn't go through the center, then it always wants to hang down like that. And it's really hard to get it to go around. In fact, it's not going to go around. Whoops. I'll have to remake that one. Okay. All right, so there you go. There's those demos. Now let's look at the new posters I got today. New posters. Oh wait, no, hold on. I do have a couple more demos. Wait, do I have? Well, here, let's do some posters here. All right. So what's some items you can put on a circuit? Now, most of these you guys are familiar with. Okay, you guys know voltage source, there's your battery, you guys know resistors, like bulbs, right? We talk about switches and fuse, you guys see those, right? Today we're going to get to these two. In fact, you guys kind of saw that one, right? So the motor demo, the electromagnet demo, right? You guys saw those. Okay. Also show you guys some capacitors. Right. Yeah, let's look at a battery real fast before we get to capacitor. So what's like inside a battery? Now, not all batteries, but this could be a battery. This is a classic conventional battery. Got a cathode and an anode. Right? So there's a potential difference between these two. What chemicals could be inside? For example, manganese dioxide and zinc is a way you could create a battery separated by an electrolyte like potassium hydroxide. Right, now, if you just leave that sitting on the shelf, then ideally there's nothing going on. It could just have a shelf life of like many years. Right? But if you can somehow get this positive and negative connected, and ideally going through a resistor, right? So then short out, right? Then now that potential difference is going to drive a current, and there's a chemical reaction that happens inside the battery. Right? So ultimately, what happens is that there's an oxygen that leaks over into the zinc, and this becomes zinc oxide. And if you run the course of the life of the battery, then at the end you'll have a bunch of zinc oxide, things like dimanganese trioxide, I think is what it is, right? And that would be an extended battery. Right, so that'll store energy in chemical bonds that you can turn back into electrical and possibly mechanical if you have like a motor or something, right? Right, now, here's another way you can also store energy, but this is in electric fields. Right? It's called a capacitor. And all it is, very simply, is just two parallel plates, right? Two parallel plates. I've got video demos for this too. I'll show you guys the video demos later. Right? You have two parallel plates, run a current through it. You'll build up a static electric charge, and it'll store some energy. Right? What's the capacitance? Let's say that's a charge per voltage. Right? You can store energy. So here's energy stored 1/2 times capacitance times voltage squared. Right? It also causes voltage to lag inside your circuit. So if you have a circuit with a capacitor, if you close the switch to turn it on, right, the current starts flowing. The voltage, it'll take a while to build up. Right? And also, if you open the switch to turn the circuit off, it'll take a while for the voltage to release. Right? If you have an electric appliance with capacitors in it, say you have an old TV set, and you're like, hey, I'm curious, I want to see what's inside this TV set. You take a screwdriver and start unscrewing it and pulling it apart. That could actually be dangerous, even if the set is not plugged into the wall, because there could be significant energy stored in these capacitors. Okay? Kind of an example here. So actually, this Faraday flashlight is a lot of parts of today all together. Right? I got a magnet running past a coil of wires like an inductor. Right? If I shake that back and forth, that'll actually generate electricity. So more on that later. That's the later part, right? Okay. But where's that energy going? Because there's no conventional battery in here, but there is a capacitor. Right? This right here is a capacitor. So shake this back and forth, right? Converting mechanical energy from my hand into, well, ultimately it's being fed into this capacitor. So that could turn the light on. So there you go, turn the light on. There's a Faraday flashlight right there. Right, right. Another fun detail about capacitors is that the rules for series and parallel are exactly opposite of what they were for resistors, right? So two in series, you treat like two guys painting a fence. Two capacitors in parallel, you actually add together. So that's opposite of what we've been doing for resistors. Okay, guys remember that? Right. Right. So see some video demos later. But see that later. Right. Inductors. Okay, this is going to be a real star of the show today. Is what if you just have a coil of wires like wrapped around, right? And you guys saw I made an electromagnet out of that. Turned this sort of into a motor. You guys saw a motor, right? And if you have one of these in your circuit, right? You guys see this later too. I've got a video demo that shows data on this. So here's an inductor in your circuit. If you have one of these and you close the switch, the current turns on. The current actually lags. It takes a while for the current to build up. So if this resistor was a light bulb, it might actually start out dim and like slowly brighten. And then if you open the switch to turn the circuit off, right, the current will still continue to flow if you have an inductor in your circuit, right? Not forever, right? But that light bulb might like slowly dim and then turn off. So it won't turn off immediately. It'll like slowly dim on, slowly dim off, right? So like a current lag. That's what this is showing for like an alternating current, showing the current lagging the voltage. Like that. You store energy. Okay, so 1/2 inductance times current squared, something like that. Right. Oh, and for series and parallel, they follow exactly the same rules as for resistors. Right? So two in series, just add them just like resistors. Two in parallel, treat like two guys paint the fence. There you go. Or inductance. Right. Right. Oh. Now you can take an inductor and a magnet, and you can generate electricity. Right. Actually, let's put this all together with this right-hand rule. Right. Here, what I've got, guys. What does I stand for? Current. Yeah, current, and you could quantify that in amps. There you go. There's current in amps, right? What do you think B stands for? Like a magnetic field, right? So B is magnetic field, right? That you can quantify in Tesla. So magnetic fields in Tesla. I know I have a poster. It says all the units of these. Right, got it right here. Right. And so here's how all these units break down. Capacitance in farads breaks down into coulombs per volt. Inductance in henries, that's joules per amp squared. Magnetic field in Tesla breaks down to Newton per amp meter. Is what that breaks down. Okay, so if you're curious about units, there you go. Okay. And okay. And then F could be a physical force, and that could be in newtons, right? And these are all related by what's called this right-hand rule. So if you know the direction of your current and you run that past a magnetic field, that will generate a physical force. That's the motor that you guys just saw. Right? You guys saw that motor spinning? That was that, right? Also, this L represents length. So what if you have a wire that's like 10 meters long and it's running like so many amps through it, and that's an Earth's magnetic field? That will actually create a little bit of a physical force. So if you have a wire that's running east-west, has some current running through it, there's a little bit of a sideways force on it. Right? You can calculate, right? So that's one application of right-hand rule, but you can also get this other ways. So if you force a current into a loop, that will create a magnetic field. That's that electromagnet I was just showing you. Right? I could pick up paper clips with the this electromagnet if you do that. Right? And the third application of this right-hand rule is if you force a magnetic field past a wire, that will generate an electric current. Right? That's called a generator. Right? That's what I was doing right here. Like if I have this magnet running past this wire, right? I'm generating electric current, which again is feeding into this capacitor, and then I can turn the light on. Now, hand in hand with that is something called Lenz's law. I have a really good video demo for this too, but I'll show you guys the live demo first. Right? So if you run if you're forcing a magnet field past a wire, right, that should generate electric current, well, that's like transferring energy onto the electric current, right? But you don't get something for nothing. And so what pops up is something called Lenz's law. So here I got some magnets, and I got this copper tube, right? Now, guys, are magnets ferromagnetically attracted to copper? No, and you guys are seeing that right here, right? There's no magnetic attraction, right? But funny thing happens when the fact this is a closed loop is important, right? When I put these magnets inside this closed loop, right, and I let this fall through, and you can see through this window what happens, right? Right. So it takes forever for these magnets to fall through, and it's not because of friction. Well, maybe a little friction, but that's not the main driver. Right? The main thing is making them take forever to fall through is that as these magnets are falling, they'll create what's called an eddy current, which will create its own magnetic field, which resists the original magnetic field. Right? So there's a physical force, like an extra physical force it takes to push these magnets through. And I've got a really good video demo lined up in a few minutes. You guys got to see too on that one called Lenz's law. Right? And that's consistent with conservation of energy, because if it weren't for that, it's like, well, how are we getting this extra energy that's on the electric grid? Okay. It takes some extra force to inside a generator. Right? Faraday's law says how much voltage can you generate from running a wire past a magnet. So here I got magnetic field, B magnetic field. I'm running past this inductor, this coil wire, being an inductor, right? And if that magnetic field is moving in and out of that wire is moving in and out of the magnetic field, right? Either way, that will generate some voltage. Here I use a different symbol for voltage. You might possibly see this in the future, say like take physics in college. Greek letter epsilon sometimes. I know we've been using capital V for voltage, but sometimes you see Greek letter epsilon, so I went ahead and threw that in here. Right? So we're looking at rate change of flux. This is calculus notation for rate change of flux. And what is flux? It's just magnetic field times area. So I got this area, got this magnetic field. Again, I've got an animation for this later. You guys will see, right? Right. And if that's changing, right? So changing. So we're implying something's moving past each other, right? Wire past the magnet, magnet past the wire, right? And then one more detail is this N is the number of coils. So notice there's like some number of coils here. If you had one coil, that might generate like some number of volts. Let's say 1 volt, right? Just to keep it simple. 1 coil, 1 volt. If you do like 2 coils, you get like 2 volts. You get 3 coils, you get 3 volts. Okay? Now the catch is, of course, that Lenz's law is also building up. So you feel, if you were physically moving the magnet, you would feel more and more of a resistive force, because now there's like more and more energy transferred into electricity. Okay? And so here's 2 of these main ideas we're getting from right-hand rule. Right? So I don't have electromagnetic up here, but how about a generator and a motor? A generator and a motor are effectively identical devices, but they're doing exactly opposite processes. Right? So a generator, we're taking mechanical energy and converting into energy of electricity, right? On a current. A motor, we're going to run that electric current and take its energy and convert that back into mechanical energy. Think like a ceiling fan, a blender, right? Anything where you plug the appliance into the wall and it causes some kind of mechanical motion. There's a magnet, and we're running a current past the magnet. That's basically it, right? That's it, right? Yeah. So again, these like if you took them apart, you say, well, they're kind of identical objects, right? It's just opposite processes, right? So here, run through that one more time. Say you have like a paddle wheel or a wind turbine, or how about this? How is most electricity generated is by boiling water into steam. So you can take coal or natural gas most of the time, boil water, turn that into steam. That'll turn a turbine. That turbine is going to force a wire past the magnet. That's electricity generation. Right? Create some voltage. There's Faraday's law. Right? All right. Now we got energy on the electric grid. Right now we can hook up appliances to electric grid. Just very simply, you run a wire past a magnet, and that will create a physical force. Right, so that's a motor. Okay. Yeah. Inductive coupling. I will show you guys a video later today of how you can transfer energy wirelessly. If you have an inductor on the left side and a separate inductor on the right side, notice this red and this green lines are separate. They're not touching each other, right? Then any electricity you run through this inductor on the left side, well, that'll create a magnetic field. This inductor on the right side picks up that magnetic field and it converts it back into a current, right? But that current changes, right? The current in amps changes and the voltage also changes, right? So if I'm going from left to right, notice a large number of coils to a small number of coils, I can tell you that I'm stepping down the voltage. And this is a really useful mechanism. The mechanism is called a transformer, right? The principle is called inductive coupling, right? So transformer, right? These are used all over the place in electric grid. So I think a few days ago, I told you guys electric grid, we're on alternating current. Those power lines that are transmitting electricity might be like thousands of volts, but a very low current. So you want high voltage and low current. But when you transfer that electricity into, let's say, the school or your house, you want to step down that voltage from thousands of volts to maybe only hundreds of volts, either 120 volts or 240 volts, depending on your perspective. Maybe some hundreds of volts. Okay. So you might have like let's say 100 coils on the left and 10 coils on the right. That could step it down by a factor of 10. That's what this formula says here. So from left to right, this would be stepping down the voltage, right? Because I'm stepping down the number of coils. I'm also stepping down the voltage, exactly proportional to that. Okay? Now, current does the exact opposite thing. Current is going to increase. So we're going from a low current on the left, so high voltage, low current, to low voltage, high current on the right, right? So current steps the other way. And if you put these two together, you can show that power is conserved, right? Which is energy per time. So that also goes hand in hand with conservation of energy. So you aren't creating or destroying energy. You're just stepping up or down the voltage, and then current does the opposite. Right? You guys remember Joule's law, P equals IV? That's what I meant to mention. That's how you can prove that energy is conserved. Joule's law, P equals IV. Okay, power is current times voltage. Okay. All right. I think I showed you guys this the other day. This engineering practicality. There's this three-phase alternating current we use, right? So that at some point you always have some voltage, right? It's not exactly constant, it kind of oscillates, but at three-phase, there's always some voltage going on, and it never goes zero. Right? And one last poster I have. This is definitely beyond the scope of high school, but if you go into, let's say you become electrical engineering, like go that route in college, or like grad level physics, you're going to see these Maxwell's equations. This guy, James Clerk Maxwell, back in the 19th century. These describe all of electromagnetism, right? And Einstein was actually looking at these, and these also helped Einstein formulate the theory of relativity. So fun fact there. Okay. All right, so there you go. Showed you guys some live demos, showed you guys some posters. Let's switch over to video demos for the rest of class. Video demos.